So we're back. At the end of the first part of this course session, we identified the second step in the algorithm for solving systems of linear equations. Remember, step one was forget about the equations, or at least, well, don't forget about them, but turn them into matrix form, into this augmented matrix. The stuff to the left of the solid line was the system of linear combinations. The stuff to the right was the coefficients, the constants that you want each of the linear combinations to be equal to. Excellent. Step two, we identified a form of nice matrices. Those are the matrices that we want to turn our matrix of coefficients to. And these are the so-called row echelon matrices, and in particular, the reduced ones. We saw it. Oh, yeah. Thank you. Sorry. For the people at home, I forgot to turn on the screen in the lecture room. So the people at home were actually watching more. So there we are. I was just reiterating what we have just done. So what we are missing now is really the heart of the algorithm. How do we go from our augmented matrix to one where the system, so the part of the matrix that corresponds to the original collection of coefficients for the linear combinations, is in reduced or row echelon form? Well, we use the so-called Gaussian algorithm, which essentially is nothing but use the elementary operations, because we know they preserve the set of solutions. What the Gaussian algorithm does is to say, okay, forget about rule of thumbs, just follow the steps. And what are these steps? There are these 5 ones that you see here. Let's go through them. Step number 1. If the matrix consists only of zeros, you can stop. It is in row echelon form. Otherwise, this means that there is at least one row which doesn't consist of all zeros. You just go through that row from left to right, and you find the first non-zero entry. Say it's A. The first thing you do is to move the row containing that entry to the top position, which corresponds to applying one of the elementary operations. You can swap 2 rows. Once we've done that, we want to turn the A, which is the first non-zero entry, into a 1. How do we do it? By applying an elementary operation. Multiply that row by 1 over A to create a leading 1. Because we want every first non-zero entry to be a 1. If it's not a 1, we make it a 1. Now, what is it that we want to do? Okay, all of the rows below must have zeros under the 1 that we've just created. Why? Because we want the matrix to have that staircase form. So for the rows below, if there is something which is not a 0 below the 1, well, it has to become a 0. Otherwise, there is no staircase form. Otherwise, we just go down. How do we do it? Well, by applying an elementary operation. You can add appropriate multiples of the first row to the rows below it. So for instance, if below the 1 there is a 3, we will add to that row minus 3 times our first row to that one. Okay, so now what we need to do is to repeat steps 1 to 4 on the matrix that consists of the rows that remain, the rows from row 2 downwards. And we keep doing that until we stop. Yeah, this is for row. So the question is, how about if we want to make the matrix reduced? So this is for row echelon form. If you want to make the matrix reduced, once you put it into row echelon form, you just basically add appropriate multiples of the lower rows to the rows above them. Absolutely. So we are making them using the Gaussian algorithm into row echelon form. Now, you can then solve the system using the system of equations using backward substitution, or you can apply the Gauss-Jordan algorithm that requires putting the matrix into reduced form. Absolutely right. In practice, actually, it turns out that the Gaussian algorithm is slightly more efficient. Question? So the question is, do you start by taking the first row or all columns? So you take it row by row. But to determine which is the first row that you want to have, if you start looking at the columns and you pick the row where you find the first non-zero one. If there is more than one such row, you can pick the first one that appears in the matrix to resolve ties. It really doesn't matter which one you choose, but let's make it the first. Now, this is make no mistake, this is a recursive algorithm. It's a recursive algorithm. Why? Because you're applying steps 1 to 4 on recursively on smaller and smaller matrices. And when is it that you stop? You stop when either you're facing a matrix which only has zeros, or there are no more rows to consider. So you either stop at step 1 or you stop at step 5. When the matrix consisting of the remaining rows is empty, there are no more rows. Okay? Now, this requires a fair amount of calculations. And you know, it's easy to make mistakes when you make calculations. But fortunately, you have algorithms for doing that. That's the reason why we actually code them. The machine doesn't make mistakes. You can make mistakes in programming the algorithm, but once you program the algorithm right, the machine doesn't make mistakes, typically. Okay, so this is how it works. So let me show you how you can use this. Well, actually, there are... let's do an exercise first. So here's an augmented matrix. What we want to do is you put it into row echelon form using the Gaussian algorithm. So we can do it by hand. Let's do it by hand once in our lives. Scratch pad. So 2, 0, 1, 3, 1, minus 1, minus 1, 1, 3, minus 1, 0, 4. Okay, so this is the matrix that we want to turn using the Gaussian algorithm into row echelon form. Let's do it into row echelon form. Okay, so what does the algorithm say? Okay, start looking, find the first column where you find a non-zero entry. Well, that's easy, it's the first column. Okay, so we want to put a 1 in this position. The algorithm says divide by 1/2. Or sorry, multiply by 1/2, sorry, divide by 2. Okay, so that's what we do. We take 1/2 times the first row. And let's see what happens. This becomes a 1, this becomes a 0, this becomes a 1/2. This becomes a 3 over 2. This becomes a 1, stays a 1, because here we haven't done anything at all. Okay, so we got a 1 now in the right place. Now what we want is to use the step of the algorithm that says, thou shalt have zeros below the 1. So how do we do it? We just multiply -1 times multiply the first row by -1, and then we add the resulting row to the second row. We multiply it by -3, and we add it to the last row. So let's do both things at the same time. So we are going to take -1 times the first row, and we add it to the second. And we're going to take -3 times the first row, and we add it to the third. Make no mistake, this is boring, but let's go through all the steps and all the pain for once. Then I'll show you a neat tool so that you can check your answers, if not solving your exercises directly. Okay, so this becomes 1 minus 1, 0. Fantastic. This is a -1. And here we have -1 minus a half. So it's -3 over 2. And here we have 1 minus 3 over 2. So we have -1/2. Let's do it again. 3 minus 3 is 0. -1 stays -1. And here we have -3 times, so -3 over 2. And here we have what am I saying? -3, so that's what have I done here? It's -9 over 2. 4 minus 9 over 2, please help me. It's, Fantastic. Thank you. Okay. So, anyway, the calculations are not the important part here. I told you it's boring. I'm already falling asleep. So what is it that we want to do now? Now we recursively apply the Gauss-Jordan algorithm on the matrix, the results, by forgetting about the first row, because we've already dealt with that. Okay? So now we look at the smaller matrix here, and perhaps I should have made it green. So let's make it green. Okay, so we want to get a 1 here. So what is it that we need to do? We need to multiply that by -1. Oh, sorry, -1. So this should be a 1. 3 over 2, 1/2. And we haven't touched the last row. Okay, now we want to get the 0 under the 1 that we just created. But that's easy. We just add. That's why we have machines to do these kind of things. We take R2 plus R3, and we write it instead of R3. So we have 1, 0, 1/2, 3 over 2, 0, 1, 3 over 2, 1/2. And here we have 0, 0, 0, 0. Okay, so now the algorithm says, look at the matrix that you have below. But that's only zeros. So we stop. Okay, so now we look at this matrix and we realize that this matrix has 3 rows, which says we have 3 equations to begin with, 3 columns, which means we have 3 variables, but one of the rows now is all zeros, which means that we have 2 leading ones. These are the leading ones. And the number of leading ones in a matrix in reduced echelon, in row echelon form, is called the rank of the original matrix. The rank of the matrix that we started from is 2 because it's reduced row echelon form as 2 leading ones. That's the number of leading ones. However, we have 3 columns, which means we have 3 variables. This means that we have what is called a free variable. A free variable is a variable that does not correspond to a leading one. So in this case, the variable x3 is free. The fact that it is free means that it can take any real value that we want, and depending on the real value that we assign to x3, then we get solutions for x1 and x2, which corresponds to the 2 leading ones. So this is an augmented matrix that represents a system of linear equations that has an infinite number of solutions. And you can choose whatever value you like for x3, and once you've chosen a value for x3, you get values for x1 and x2 in terms of x3. Let's spell this out. x3 could be any real number. But once you fixed x3, what is x2? Okay? In order to determine what x2 is, you can look at the second row here in the reduced row echelon matrix. The second row tells you that x2 plus 3.5 x3 should be equal to 1/2. So in other words, that x2 is equal to 1/2 minus 3.5 x3. So you can see that the value of x2 is a function of x3. Give me a value for x3, I'll give you the corresponding value for x2 in the solution, where x3 takes that value. Similarly, what is the value for x1? Well, the first row here says that x1 should be equal to 3/2 minus 1/2 of x3. Again, you can see that the value of x1 in a solution depends on whatever value we assign to x3. So in other words, the value of x3, so the set of solutions, is a function of x3. So what are the solutions here? The solutions are going to be all of the triples of real numbers that take exactly this form. 3/2 minus 1/2 of x3, 1/2 minus 3/2 of x3, and x3, where x3 is any real number. And this is sort of the solution set. You can see there are infinitely many such triples of numbers. So for instance, when x3 is 0, x1 should be 3 over 2, and x2 should be a half. When x3 is 1, then you get x1 should be 1, and x3 should be minus 1. Okay, so important message of this example. That's the only important message, not the calculations, because those machines can carry out for us. If once you put your system of equations into reduced row echelon form, or simply in row echelon form, you have a number of leading ones which is smaller than the number of variables, and you don't have rows that indicate inconsistency, like rows of the type 0, 0, 0, 0 should be equal to 34, which is not possible to a non-zero number, then you have an infinite number of solutions. And the free variables, the variables of which the other values of the leading ones, the leading variables, will be a function of, are all of the free variables that you can freely make range over the collection of real numbers. And this tells you in yellow what are the leading ones, and it will also tell you how to express the solution set, in this case with a free variable, which is x3. It tells you x3 could be an arbitrary real number, and once you fix what x3 is, here's what x1 and x2 will look like. You can find a link to the linear algebra toolkit from under other material on my school. I encourage you to play with it and to use it to check your calculations, because making errors in calculations is easy. Of course, you can also use the linear algebra toolkit to solve exercises that I give you and copy the solution. However, if you do that, you don't learn anything. So it's a good idea to actually try to solve it yourself and then use the linear algebra toolkit to check your answers. Personally, I don't care whether actually you end in what the linear algebra toolkit gave you, but then you have to ask yourself, why am I doing this? So you're here for learning something, not to put stuff into a magic box that gives you all the answers. Unfortunately, at the exam, this thing will not be allowed. And you will not need it, because I'm not going to ask you to solve mind-boggling systems of equations for those who have machines. I'm just interested in seeing that you understand how to go about doing that. You may note one thing that the linear algebra toolkit says here. Look at this reduced row echelon matrix. No equation in this system has the form 0 equals non-zero. Therefore, the system is consistent. If at any point, when you're manipulating your augmented matrix, you end up with an equation with a row of the form 0, 0, 0, 0, solid line, non-zero number, then you know that you don't have any solution. That's a telltale sign for an inconsistent system. And at that point, you can stop and say, no solutions, Luca, or whoever. Actually, the linear algebra toolkit can do lots of good stuff for you. You can do all of these things, some of which will not be necessary for this course, but for some of you who might be taking the linear algebra course, you might be interested in looking also at those. For us, basically, this is all that we will need. And you can also practice. You see there is a row operation calculator, transforming matrix to row echelon form, transforming matrix to reduce row echelon form, and solving systems of linear equations, which is something that you will be bored with within a few minutes, and calculating the inverse of a matrix using the row operations. As you can see, you understand the row operations, you can do everything, nearly, apart from some of the things that we'll be doing later on. Okay, so I give it to you. Play with it and enjoy it. Unfortunately, it doesn't grade the assignments. Otherwise, it would be perfect, like the automata tutor, but there you are. Okay, so so far so good. In fact, we've already done this type of things. So you can take a system of equations like this, and when I ask you, describe the set of solutions, what I want is a description like this one. You basically figure out which ones are the free variables. In this case, in this example, it will be z, and you express all of the solutions as a function of the free variables. Like I've done here. People are really getting sleepy in the room. So shall I start jumping around, sing, dance? What else do you want me to do? I should probably do that. Unfortunately, this is a little bit more complicated to do with this material than with the theory of computation stuff, where we can call about oracles and stuff like that. But let me try to be perhaps funny. Today I haven't been that funny myself. That's probably because I'm chasing a deadline, which is tonight. Okay, fantastic. No more of these exercises. You can use the linear algebra calculator, or you can do that at home. So let's look at the conceptual part. I told you we are going to use an algorithm which is called Gauss-Jordan elimination to solve systems of linear equations. In fact, we've already seen the algorithm. What is the algorithm? Give me the system of linear equations. Transform it into an augmented matrix. Now you use the Gaussian algorithm to turn it into reduced row echelon form using elementary operations. If you have a row of the form all zeros, 1, then the system is inconsistent. Now you may say, okay, wait a minute, Luca. Before you said, if you have a row of the form all zeros, solid line, and that's where the coefficient, the constant start, some non-zero number, then you're inconsistent. And now you're saying, or a row that is all zeros, 1. What if I have 35? You divide by 35, and then you make it a 1. So there you are. You mean we are binary, so we don't like numbers which are not 0 or 1. Yeah, well, actually, we need to use them sometimes, but with sadness in our heart. Anyway, let's turn all the stuff, all the constants into 1. So if you want to determine inconsistency. Okay? If there is no row that looks bad, like 0, 0, 0, 0, 1, then you know your system is consistent. Okay, now you have a choice. Do you have one solution or infinitely many solutions? There's nothing in between. Okay? How do you determine whether your system has infinitely many solutions or one solution? Okay, you look at the number of leading ones. If the number of leading ones is equal to the number of variables, then there is only one solution. If the number of leading ones is smaller than the number of variables, like in the example that we looked at before, then you know you have free variables. Variables that can take an arbitrary real value in any solution, in a solution. So in that case, you know that you will have infinitely many variables. Infinitely many solutions, sorry, not variables. There are only finitely many of those. And you determine the collection of all of the solutions by expressing the solutions as a function of the free variables that can take any real number as value. If you're using pure Gaussian elimination, in the first step, we just turn the matrix into row echelon form, not reduced row echelon form. And then you use back substitution to calculate the values of all of the variables in a solution. And if you look at it from the eyes of numerical analysts, who are the guys who devise these kind of algorithms and implement them, this is slightly more efficient. Now, the question I typically get is, when I'm solving a system of equation using this type of algorithm, shall I actually turn my matrix, augmented matrix, into reduced row echelon form or not? Well, it depends on whether I ask you to do so or not. So if I say, turn your matrix into reduced row echelon form, or in other words, use the Gauss-Jordan elimination algorithm, then you do so. Otherwise, you do whatever you find simpler. There is free will, unless I remove it from you. Okay, so the question is, how can we tell whether the number of solutions is one or infinitely many? Well, I assume that you already figured out that the system is consistent. So there is no bad row that looks like this. The next step to do is you count the number of leading ones in your row echelon matrix. If the number of leading ones is the same as the number of variables, there is only one solution. If the number of leading ones is smaller than the number of variables, then there are free variables. So there are infinitely many solutions. And the set of solutions can be described as a function of the free variables. So, example, I think that some people are not overly convinced. Since I don't want to calculate too much today, I've already done enough of those. Let's use the tool. So let's, for instance, let's do 2 equations in 3 variables. Why not? And let's say that we have something that I never tried before. So this time I didn't cookies. I'm just making it up. Okay, give me some numbers. Let's be quick, because otherwise I do it for you. Okay, there you are. I've done it. So 2 equations in 3 variables. Okay, so what is the largest number of leading ones that we can get in the reduced form? 2. Why? Because you can have at most 1 leading one per row. You only have 2 rows. You have at most 2 leading ones, 3 variables. What do you expect here? Could there be exactly one solution? Sort of no. So there are 2 possibilities. Either the system is inconsistent or it has infinitely many solutions. Let's see. So you look at the reduced row echelon form that the system actually calculated with us, and it has 2 leading ones. There is no bad row, no row of the form 0, 0 equal to something non-zero. In fact, there is no 0 row in this part of the matrix. So we know that there are infinitely many solutions. What do they look like? How can we describe them? We realize that the variable x3 is free. Why? Because it's not a leading variable. The leading variables are x1 and x2. So x3 is a free parameter. We express the values of x1 and x2 in a solution as a function of the value of x3. So we set x3 to be an arbitrary real number, whatever number you like. But once you set x3, then x2 should be computed by setting that value of x3 in this expression. And x1 will be 3x minus 3x3 plus 6. So for instance, if x3 is 1, x1 should be 3. If x3 is 2, x1 will be 0, and so on. So this expression here describes all of the possible values of the solutions, all of the possible solutions. There are infinitely many because x3 can be an arbitrary real number. Okay, the question is, if x3 were a leading one, would the system be inconsistent? Well, if x3 were a leading one, then either x1 or x2 would not be a leading variable. In that case, either x1 or x2 would be a free variable. So for instance, for a different system of equation, you could have a 0 here and a 1 here. So you would have this last row could be 0, 0, 1, and then it's x2, which would be a free variable. The system can only be inconsistent if you have a row that says 0, 0, 0, 1, or non-zero value in general. Okay? So I think according to the clock that I have here, it's time to wind up the lecture. What is it that we've learned today? We've learned today how we can program a computer to solve these bloody systems of equations for us by using the Gauss-Jordan algorithm. Take your system of equations, construct the augmented matrix, apply the elementary row operations as instructed, look at what you get, and decide whether you have 0 solutions, 1 solution, infinitely many. That's all you need. Thank you.